This whole topic here, you'll get this online. Right. So you would recognize that a few of them would deflected, right? So basically, this experiment is a Geiger-Marsden experiment, right? And they use this gold foil experiment to observe the atom. And when they shot the alpha particles, that's the little purple particles, they observed three things. Most of them went straight through, an extremely small amount was deflected, and an even smaller amount was reflected, which meant three things about the atom. The atom has empty space, the atom has a small positive core, right? And the atom's small positive core is dense, solid. So when it hit it, it reflected. Right? You'll see the particles that reflect. Tell me when you see one. Not deflect, one that reflects. Right? None as yet, huh? See that deflection or straight through. Any as yet? Right? So it's a very, very small amount. Nobody reflecting? No, that's long. Yeah, it just kind of deflected, coming close and it deflected. Yeah, we had some, I saw it in the beginning. That one was close.
The ratio for every number.
Yep, it's like a percentage, it's like 97% going straight through. 2%. Let one come back there. See him? Sorry, on the left. One came back there. Okay, so that was a Geiger-Marsden experiment that they did it in the Rutherford lab, right? Okay, so let's go back to the notes. All okay with that one line? What the experiment was about? I know it's a little slow there. I wonder how it is. Did you all ever watch the videos?
No, about
like watch the videos and see how when I do a simulation, how it does look. I don't watch one, right? I don't even watch them. I don't watch one. I'll come back later and I'll watch this video. I just want to see what the simulation looks like. If it's slow like this, or if it. Right. So let's talk about this physics of the atom, right? Who's Adele? Adele, your phone always on. Every time I have Bluetooth, your phone on. Play a message in there. I thought it'd be on when you're using it. It is always on. All right. Okay, so this here is a small this is a design of it, right? The gold foil in the middle, alpha particle, and there's a deflecting screen around it, right? Right. So Geiger-Marsden, right, sometimes called GM, right? Geiger-Marsden experiment established the nuclear structure of the atom that we currently study. The apparatus was set up as shown below. So you have your alpha emitter, you have your gold foil, and you have a detecting screen, right? Alpha particles were incident on a thin sheet of gold foil. Any idea why gold? Any idea why they use gold? Gold foil, thin sheet of gold foil. Any ideas? Anybody online? Barrage, any ideas? Why do you use gold foil? Right, very good. Shannon, Google that or?
Definitely.
Right, yes, it's malleable. Right, because it's a metal, you have the ability of actually sheeting it out something nice and thin. Right, and it wouldn't break. Right, so you have the ability of changing the shape of gold. And also, gold is a bit inert, it's not really reactive. Right? So good, very good, Shannon. Good Google in there. Good Google in there, Shannon. I think that's quick word. Right? And the behavior of the alpha particles were noted. Hey, you don't want to write it yet or the handout. Just pay attention. I'll ask the question just now. Right? Everything in this handout. Sorry? right? And the behavior of the, you can make a little note in it. Yeah, that's a good idea. It's a good habit to develop, right? Thin sheet and behavior of the alpha particles were noted. Remember that alpha particles are positively charged helium atoms. They observed the following. Number one, most were deflected. So I kind of make up a number, right? 90%, but it's a little bit more than that, right? 90% were undeflected, 7% were deflected by smaller angles, and a few were surprisingly reflected or bounced, right? About 3%. Right? So this is kind of how it looked, right? Kind of looked like that. Most of them going through, a few deflected, and one basically reflected. Their conclusions from the above results were as follows. Since most of the alpha particles passed straight through, then the atom was mostly made up of empty space. From the alpha particles that were deflected slightly, it gave the idea of the atom's central core being positively charged. So the first conclusion was this, empty space. Second conclusion, the core was being positively charged, right? Since a positively charged alpha was repelled by a small angle, right? Remember, like charges repel, unlike charges attract. The few particles that were reflected appear to have some sort of head-on collision, resulting in the conclusion that the atom's core was small and dense, right? So the three conclusions were, right? Number one, small and dense. Number two, positively charged core. Number three, empty space, right? So if you're making your notes, it might be hard for you to remember this, but you should be able to remember empty space, positively charged core, and the small and dense. That's okay? If you want to make your own notes, now's a good time to take the pen and make your own notes. Right? Do it quick. Quick. Huh?
Right.
This is how Geiger and Marsden came up with the model of the atom. This, if you want to be specific, this is the conclusion of the gold foil experiment. Right? So make a note of them. Right, make a note of those. Hey, you see what I done? You see what I done? Me. Nice to see you, man. Nice to see you. What do you say downstairs? So sort it out. What is that? You still give me a 0? Come on, you will see. Right. Finish. Right. So this is basically what the atom looks like. The one that we know today. We have a center with nucleus, and we have shells with what we call electrons, and nucleus with protons and neutrons. Right. Normally at this time, I'll ask you to do a quick little Google. I want to see who's the fastest. Here's what you're doing for me. Take out your phone. So you get a chance to use your phone in this class. Here's how I to do for me. The first person to tell me, you might have to turn on your audio or somehow it might be faster that way. Right? I want to know who came up with, who found the protons, who found the neutrons, who found the electrons. Yeah. I want to know who found the neutrons, who found the protons, who found the electrons. Chadwick is which one?
The electron.
I want all three together. You can't tell me one at a time. Shannon don't Google it. Shannon, wait, Shannon, you copy and paste that? No, Shannon, your own type, you can't do that. So I want to see neutron, who it is. I want to see electron, who it is. Yeah, no, but I don't want to just Google it thing and copy it and paste it in the chat. Tell me who found the proton, who found the electron.
And Ernest found.
Who's Ernest?
It's not certain this stuff.
Nice. All right, so let's see. Right, election was who? Wow, where's Sudo?
Thompson. J. Thompson.
Right, so J. Thompson.
The protons are Eugene Goldstein.
Right, nice. Who was Proton?
Eugene Goldstein.
Ah? Ernest who?
Women discovered positive patterns of
Huh?
DNA.
Rutherford, right? He's the most one of the most famous guys in this
Yes, two of them.
in this field. Yeah, but learn Rutherford, right? You'll see that need multiple choice. Right, Rutherford and neutrons is who? Right, Chadwick, right? It kind of difficult to me. It kind of difficult to remember the first name. Those the last names kind of connected with the particle a little more. So once you hear neutrons, you know Chadwick. Once you hear protons, you know Rutherford, right? And Thomson is the electron. Right, but who was the fastest? Shannon. Right? Well, the man wins.
Sir, it don't come because you're not there.
By time all still standing one, Shannon said all.
Say, don't think he happy book, sir. Don't think they in school and happen.
Well, send it first, send it back. Well, you'll do something in school?
Nah.
Oh, no,
Why?
them don't do it either.
Where?
Shannon
So
said,
you sound good. No, it's on a day.
man, quick on the draw. Nice, make a note of that, right? So the three particles that inside that make up an atom are protons, neutrons, and electrons. Okay? In chemistry, okay, all right.
Yeah, see? You go in chemistry lesson. You know what I did?
You say you get the names in chemistry.
Yeah.
I can't remember hearing this in chemistry. Huh? I remember hearing this in physics. Right, make a note here because they like to ask this in multiple choice. Make a note already? Note game on points for it. Is there any more game sense or? Huh?
I'll give tomorrow.
All right, like so.
No, but yeah, you see, the game.
Come on, jump here.
That's not very young. Yeah, that's
Who is that?
Rena.
Is the other one?
Oh, this. Myself.
Yeah.
Especially in the
We playing, but what are playing? What are playing?
That is easy lecture. We beat them.
All right, good. All right, Samir. Why, Samir? How come your messages come in here? I don't understand. All right, so structure of the atom, right? The atom, as discussed before, with the aid of a few more experiments, contains two more components, right? The nucleus, which contains the protons and neutrons, and the shells, which contains the electrons. Are you okay with that? All right. The proton has a mass. Well, this is the relative mass, means when they compare them to each other, right? But the values that you will use: proton mass of 1, neutron mass of 1, electron 0. And these are your charges, right? Proton positively charged, neutron has no charge, electron -1, and it tell you where to find them, right? Right? This table important, so make a little note of this table now. Chemistry people, well, you all should know all this, huh? Nice. You doing chem too? Serious?
Say what a mistake, you know.
Yeah,
I should have
physics? Oh, not in physics?
I don't know. Oh, no, you see, if you got it.
Wait, what are you in school?
Yeah, I know.
Hey. All three?
Yes. I'm trying to.
What's the last thing out there? Aristotle. Wait, you Aristotle? Academy, so sorry, yeah. So you also know mechanics? What are these?
Lyrics nowhere in mind, but on now, like the right, the one stuff like 17 and tell you, fast to do that. That make any sense? You know, it's advising listen, right? Waves.
Waves. All right.
You know, I think
All right. So let's continue. So the proton and neutron are about the same mass, while the electron is much lighter than them both. This gives rise to the deduction that the nucleus gives the atom all the mass. So the nucleus gives all the mass, and the mass given by the shells and the electrons is negligible, right? So the electrons don't really give any mass. Oh, by the way, I think I have it later on. Oh yeah, I have it later on. The proton is positively charged, the electron negatively charged, while the neutron is neutral. So this is why the nucleus is positively charged and the shells are negative, right? Sometimes in physics, we don't call the protons and neutrons just protons and neutrons. We call them nucleons, right? Yeah, protons and neutrons are called nucleons. Okay, there's some give the mass of the atom, and we call it the mass number. So when you add the protons and neutrons, you'll get the mass number. Okay, sometimes we call it nucleon number. If the atom is neutral, the protons equal to the electrons. Okay, make a note of this little thing there. Don't try to write in note, just make a little summary, right? You know, therefore, whenever you decide to read it. Hey, sit down properly and know what are you saying now? Comfortable. That's the important. All right, good.
Why do you think
And the next person fellow who decided to come,
yeah, Levi?
but I must. Was
Probably. Is he from a fiction?
no, yeah.
He must have gone.
No, it must. And physics. Anyway, I can't remember. All right, so here.
It's a real dark color.
No, I think I can't remember. Okay, it was in the beginning. All right, so if you look here, you'll be getting the symbol form of a particle, right? Or atom, right? The A, the one on the top, is called the nuclear number, which is the mass number, and the one below is the atomic number. For example, 12C6, right? 12C6, carbon, it has a mass number. It has a mass number of 12, right? And it has an atomic number of 6. I'll ask you how to find the number of protons, the number of neutrons, and the number of electrons. Protons is always the same as the what? Right? Proton is always same as the electron and also the same as the atomic number. So your protons is the same as the atomic number, and your protons equal to the electrons. That's okay? So the protons and the electrons are always the same. How are you getting neutrons?
Mass number minus.
Right, mass number minus the proton number, which is 6. That's okay?
If you just do mass on
Well, yeah. Right? So that's basically how you work out these things. But in physics, just like chemistry, you need to be able to draw the atom, right? So we need to figure out the electronic configuration. Right? Electric configuration just telling you how to split up these 6 electrons. Right? So we need to remember this. Right? We need to remember that the first shell could only hold 2 electrons. The second shell could hold a maximum of 8. And all the other shells can do the same thing, maximum of 8. Third shell, fourth shell, and so on, right? I don't think in physics we ever gave you, Terry, come to your class. I don't think in physics we ever gave you more than the third shell, right? But anyway, it basically looks like that, right? So for example, for carbon has 6 electrons, right? So what's the electronic configuration for carbon? 2 in the first one and then 4. Are okay with that? Right? 2 and 4, because it has to add up to the 6 value here, right? So therefore, how do we draw that? 1 shell, 2 shells, right? So you put 1 electron here, 2 in your first shell, then 4 in the second, 1, 2, 3, 4. Right? You put them singly first, and you double them up. Anybody confused with that one line? Cameron, you okay with drawing the atom? Maria, you're okay with drawing the atom? Right? You have to also see what the nucleus are, right? Cameron, Maria, you're okay? Right, so the nucleus with 6 protons and 6 protons and 6 neutrons. All right, copy this down, and I'm going to give you one to do, right? Viraj, you with me still? Vishala, you okay? Viraj, you there? All right, nice, Viraj. Right, so we're doing something nice and easy, so please, if you get lost, let me know, right? So I'm going to give you one to do for my desk now, right? Same thing, I want protons, electrons, neutrons, and how to draw it, right? Cassie, Chris, Cassie, you could log in if you want to, right? Oh my God, this guy is going to finish.
Oh. Well, I guess you can take it out.
I do. I have biology.
Yeah.
Mitosis is mitosis.
Yeah, you know.
You know what it is?
No. Well, I do it. Yeah. I thought I taught my lesson.
Yeah, but it's not mitosis
Yeah.
or something?
Yeah, it's meiosis.
Meiosis.
Yeah.
Finish? Right, so I wanted to do a particle here for me. All right, and it's in black, right? Do 23 11 sodium. Right? 23 11 sodium. I want the protons, the electrons, the neutrons. And draw it. 5 4 8 1 4 3. Right, please do the same thing, protons, neutrons, electrons, and draw it from up. Those who are online, just message me how much protons, how much electrons, how much neutrons. Finished, Christian? Or doing it? No, I just asked him, are you looking suspicious? You don't show me anything? I correct Samir. Right, work out your protons, your neutrons, your electrons, and then draw it, right? Good to do this. Finish? You have a pencil, but you mind using it? You have to draw it too. have to draw it as well. Right, good job, Vishala, good job, Samir. Good job, Maria. Remember to draw it, right? Good job, Chaya.
So the 20 is the mass number, right?
The bigger one is always the mass one. Right, don't forget to send your answers. Cameron, Sahara. So when they finish, Tariq, you're doing physics too? One minute, Shannon here. Next minute, Shannon go. Is Shannon in this class? Shannon before Shannon is log on and fall asleep. I'm sure she's sleeping. I'm sure Shannon sleeping. Ah, she wake up there. Yeah, man. My image.
Yeah. You just had impressive images.
Right. Time up there. Raj, Cameron. Or should be done by now. Cameron, you done? All right, let's check this last one out. 23 sodium 11. Cameron again, should I? Protons is 11, neutrons is 23 minus 11, which is 12. Electrons is 11. Okay. Right, and electronic configuration 281. Right, so when you're drawing it, you draw your nucleus. You have to tell them what the nucleus have in it. So you have to say nucleus with 11 protons and 12 neutrons. Then draw your shell. First shell, second shell, third shell. This is 1, 2, 8 in the next shell. 1, 2, 3, 4, 5, 6, 7, 8, and then 1 in the last shell.
So then if it's too big, like we say, like 15, you don't have to make the 2 inside. From later, just try to make the outside.
Oh, you mean like give it a real big, just draw the outer shell? Yeah. You can do that too, but in physics, there's one day everything. That's more chemistry. Okay, so nice. Right, let me see who knows the chemistry.
Not me.
What has happened when a particle keeps the same proton number but changes the mass number? Same proton number, different atomic number. Sorry, same proton number, different mass number. Sorry. Right, but what is called that type of particle? Huh? Huh? It's called an isotope. Right? It's called an isotope, right? Okay. Right, we are going to study a lot of radioisotopes. All those particles that we deal with, And this topic is radioisotopes, right? Because the radioisotope is not as stable as the actual particle, right? And radiation is given off from unstable atoms, well, isotopes. All right, nice. Any questions here? Did I get anything from Barrage? Nothing from Barrage, nothing from Cameron. All right, next other questions is too early alone. All right, nice. So quick little mention here. An isotope is an element that has the same atomic number, but different nucleon number. It can also be viewed as an element with the same number of protons, but different number of neutrons. Right down there, you have two isotopes of carbon. Okay, 12C6 and 14C6. Things to note, the shell model of the atom gives the property that any element in the periodic table has one more proton than the element before it. Remember that? What's the element before carbon? Boron. And after carbon? Nitrogen, right? Okay, so those particles around it has one less or one more proton than that's called the shell model. Okay, so the shell model gives you an idea that every element in the periodic table has one more proton than the one before it. Okay, sometimes we kind of forget this, so make a note of this, right? What the shell model is. Okay, so nice. That's the physics of the atom, basically. Right? Now we're going on to we're going to focus on these isotopes and see what type of radiation these isotopes produce. All right? So as I told you before, an unstable nucleus has to lose energy to become stable. That's okay? If you're unstable, means you have too much energy, right? Anybody unstable? Huh? No, that just means you have too much energy. That's all I mean. So if you know anybody who unstable, they just have too much energy. Right? And when they no, you just say something. And when they lose the energy, then they become stable. Right? When radioisotopes lose energy, they lose the energy in the form of three types of radiation: alpha, beta, gamma. All right, alpha is that little symbol there, beta, next symbol, gamma, next symbol. Any familiar?
Gamma.
Any familiar? That's the only one that's familiar? Alpha, you just use alpha. In Geiger mass, an experiment.
No.
Right? Beta, I'm not sure whatever. You all know what beta is, but you probably never hear it.
Yes.
Yeah? Beta is what? I'm talking about that, talking about the particles. Right? And you all must have heard about gamma radiation. Right? You must have heard about gamma radiation, right, Grace? All right. Well, I told you what alpha is already. Alpha is a helium atom. Right? Beta is a electron. 0 minus 1e. And gamma is a ray. Just a ray of energy. Right? So you have these three particles: alpha, beta, gamma. Sorry, not three particles, two particles and a ray. So alpha particles is a helium atom, a beta particle is an electron, right? A beta particle is an electron, and gamma is a ray. Are you okay with that? Right? So let's learn about each one of them, right? Any questions online? Cameron, are you there? Cameron, your video working? I find you know, send working. Your camera working? I just had to make some other point on the camera. Barrage, you there? Everybody else said answer. Barrage, I need you all to send answers. Yeah, Cameron say Cameron not working. What message him mother? Right? I don't want to see her. I just want to see a book and a pen and say that I work. I'll show you the angular one. Barrow don't answer nothing online. Barrow don't answer a thing online. All right, so let's learn about alpha particles. Right, let's focus on alpha and beta. Right, one thing I want to note, just make a little note next to alpha and beta, that those two are particles and gamma is just a ray, like energy, like waves, basically, in a way. Alpha and beta are particles, gamma is a ray. All right, so let's do a little maths here. Chemistry / maths, right? Right, so alpha emission. This is in the form of a particle, alpha particle, which has a helium nucleus with a charge of +2. When an atom decays by alpha emission, its nuclear number decreases by 4, right? And its atomic number decreases by 2. So watch this here. This particle called radium, I think. I really can't remember. It underwent alpha decay. This is called alpha decay. So this particle lost the alpha particle. What will happen is that its mass number, which was 226, will now lose 4. So to become what? 222, right? And then its atomic number, which is 88, right? 88 will lose an atomic number of 2 to become 86, right? One thing you have to learn to do when you're balancing these equations in physics, you have to make sure that the mass number on the left-hand side is equal to the mass numbers when you add them up on the right-hand side. Are you okay with that? Yeah? Online? You're okay with how alpha decay will work? Yeah? Nice, Vishal. I like how you're responding. Right? You wouldn't have a pointed camera, right? You gotta keep yours off. But oh, Cameron and Viraj answer fast way. All right. This question is for Cameron and Viraj. Today, in your notes, you can take this one down.
That H was big H and big E or big H and small?
Big H, small E. Right. Watch this here, right? Everybody, watch this here. Let's say we had a particle CM, right? I'm just making up these numbers. It's not a real particle, right? 21264. And CM underwent an alpha decay, which means it will lose 4,2 helium, right? So CM becomes a VG, right? I would like to know what is X and what is Y, right? Cameron and the barrage message was X and message what you think is Y. Yeah, everybody doing it. What you can do is you can work it out. Write it down and work it out. Right? Work it out. Tell me what you think is X and what you think is Y. Nice barrage. You can keep your cameras off barrage. See how easy? Let's check out camera now. Cameron, X looking good. Tell me what you get for Y. Everybody can message. I just want to make sure I get from two of them. Nice job, Jaya. Cameron, I will take that. Cameron, you can keep a camera off. Nice. And I know your camera working, eh, Cameron. Right, how we getting X? X will be 121 minus 4, which is 117, and Y will be 64 minus 2, which is 62. Are you okay with that? Yep. Let's try one more. Good job. Nice. Let's change it up now. Let us change it up. Pull up that. Last one here. Last one here. So KY 7436 underwent 2 alpha decays. 2 alpha decays to become JB. Right? Right? It lost 2 helium particles. Try that, please. Tell me what you get for A and B. Tell me what you get for A and B. Too easy. I'm not acting next the same thing. We show you remember. Somebody asked me about a lab and I forget the message. Oh no, I did that. A message. I told her what to do. I remember. Now cash was coming up, so my phone will be busy. Get out. See, looking for forget already. Wasn't important. What? All right, let's see. Now you have 2 helium, right? So you're minusing 4 twice, right? You're minusing 4 twice from the mass number, and you're minusing 2 twice from the atomic number. You do you. I will do me, right? I will minus 4 twice, right? So you will end up with 74 minus 2 by 4, which is what, 66? And then 36 minus 2 by 2, which is that's my all right, 32. 66, 32. You got me, eh? Okay. All right, nice. Anybody confused? Samir, you okay with this? Ishana? Everybody okay with us? Okay, so this is the alpha particle. Let's take a look at the beta particle now. Anybody confused? All right, let's go to the beta particle. Right? So the beta particle, as we said earlier, the beta particle is an electron, right? 0 minus 1e, and the charge is -1. When an atom decays, the nuclear number remains the same, but the atomic number increases by 1. Anybody could tell me why? Why it increased by 1 and not decreased by 1? Oh? Because you added a -1. I don't like that. Because you're minusing a -1. So you end up with plus, right? If you add a -1, it'll still be negative. But if you minus a minus, it'll be positive. You think? All right. So you have to remember that, right? When is a beta particle, the nuclear number will not change, but the atomic number will increase by 1. Okay? Look at the example there. 14C6. 14C6 underwent a beta decay and it became 14N7. Everybody okay with that? So I'm going to give you an next one now, a combination, right? In fact, I'm going to show you gamma one time, right? Since you all kind of understand the principle, right? Last part, gamma. Look at gamma. Tell me what you notice about gamma. Take a read. What you notice about gamma? Take a read first in your mind. In your mind first. And then it divide. Yeah, we read it now, Ricardo.
Yep, I know. So there's some random detection. That's it.
And you reply?
Well, so sometimes there's a pattern. I don't know. So I wonder. I said it's a picture.
Right? What you all recognize about gamma? Right? Gamma is just a ray. So does it change the mass number? No? Does it change the atomic number? No. See that, right? So it changes nothing except it has less energy and it's stable. That's okay?
So what do you mean excited?
Excited means they have too much energy. Yeah. Okay, so alpha, beta, gamma. Right, so I'm going to give you one to try here. Tell me what happened, right? I'm watching in general location. Try this here for me, please. Right. So RE, it underwent an alpha decay. It underwent an alpha decay and a beta decay. I am not writing the equation. I'm just telling you what it's forming. Forming AL. Right? Finish the equation out for me. And the beta decay.
So
Do that, please.
and these three that is
0 minus 1.
is 0 on top of minus 1.
Come on, you finish, right? Hey, you finish? We'll write it again now. Say go ahead. Write it again.
This is the debate I mentioned. So what I'm going to like with alpha, I had it on one time. What happened to the beta?
Oh, you want to hear you went downstairs?
Yeah.
So it's happening, you mustn't go downstairs.
And the pizza,
For more important.
my bladder is.
All right, well, ask your bladder the answer. Right, the atomic number doesn't change. I mean, the mass number doesn't change, and the atomic increases up by 1. You all done? Right, so alpha is 4 to helium, beta is 0 minus 1. Right? So let's see what we'll figure out for EL. That's capital L, and not common L. What you'll get for the top part here, you'll get 150 minus 4 minus 0, which is 146. So I still writing it, right? Are you okay with that? And underneath is what? 70 minus 2 minus 1. Right? Or you can just add the 1, right? Which is 70 minus 2 plus 1, which is 69. 69, right?
I didn't say that.
But you just need the whole reaction, right? You have this whole line. I said to write the whole reaction. I said to write the whole reaction. Any questions online? Shannon, any questions? Cameron, just check back your Y value, right? Check back your Y value. Malini, you okay with us? All right, so that's the intro into all of this here, right? Alpha, beta, gamma, right? There are some more things that we need to learn about alpha, beta, and gamma, right? That's the last thing we're doing. Right, let's take a look at the table here. Anybody writing? Right. Right, so alpha, beta, and gamma behave in 3 ways, and in different ways, right? Right, Malachi? Take a look at alpha. Right? Alpha is stopped by what? Right. So if you have an alpha, if you have an alpha particle, and you want to stop the alpha particle, put a sheet of paper in front of it. Yeah? So it will collide with the particle and it will stop right there. A beta particle, what? A beta particle is stopped by aluminum, right? And gamma is stopped by lead. So I have a question. Why it is Geiger and Marsden did not use beta and gamma?
No, let me think about it.
Why they didn't use beta and gamma?
Probably didn't.
I have a few reasons, but why it is they didn't use beta and gamma? Yeah, they probably had it. Let's assume they had it. Why they choose beta and gamma over alpha? I'm looking for a nice answer. Think about what beta is. Think about what gamma is. And we'll of course think of the experiment, right? Think, like I'm giving you 2 minutes again. Think. Hey, Mr. Unstable man. Think. Radioisotope. Yes, sir. Why? $1,000. Yeah. All right, Malachi. What do you think? I won't do that. Ricardo, class going on finish in 10 minutes. You can message it person, right?
I think that it is you have to access. We are
Anybody else? Chris, what do you think? Why they didn't choose beta and gamma? China has something to do with that. Right? Anybody? Why does it choose the alpha as opposed to the beta and the gamma? Kilon, what do you think? Something to do with weight, kinda? Something to do with weight. All right, something to do with something to do with what we just talked about. Right? Those three things I understand. Why would you choose alpha and not choose beta and gamma? It has other reasons, but there's one that we can talk about. Huh? They didn't want to why? Why? That's not. Kinda. Right? But there was something important that we're missing out. Ricardo. Cheaper? No, not cheaper. All right, so in fact, no, I'm not giving you the answer. What do you think about it? Why we choose alpha over beta and gamma? Homework, right? Yeah, I want about 4 points, 3 points why. 3 reasons why. Now, how do you remember it? Write it down now. Why they choose alpha? Yeah, you can wrote you figure this right. Why they choose alpha over beta and gamma? Anybody want to have a little answer? So I want you to think about it, right? Vishala, you're close to it, but you have the kind of opposite, right? So I want you to think about that, right? Yes, for next week. All right, and yeah, so we have alpha, beta, and gamma. Beta could travel the furthest in air. Sorry, gamma could travel the furthest in air. It travels kilometers in air. Beta will travel several meters. Alpha will travel a few centimeters in air. All right. So one quick question before we go. It have a race between. Sorry. So you have alpha, beta, and gamma, right? All three of them go in a race, right? But you want gamma to win. What you could do based on what we just learned. Alpha, beta, and gamma go in a race. You would like gamma to win the race. What you could do, right? What you could do to help gamma win. Ricardo,
I really don't know answer.
Well, think, come up your phone and think. Huh? Right? You're along the right. You also see we can put these two together. Jacob said use lead or something. Shannon said to block alpha and beta. How are you doing that? What's that? Yeah. Yeah. Say it. Right. That's it, yeah. Right. So you could, but you don't even need the paper. You don't even need the paper. Just put aluminum. Right? Because the alpha will hit it, can't go beyond that. beta will hit it, can't go beyond that. And gamma will go straight through. Right? Good thinking, Shannon. Google that password. Right? Are you okay with that? All right, so for next day, I would like you to take the handout and I want you to read up on half-life and wait, that's not. I want you to read up on half-life and read up on nuclear energy. Yeah, if you don't want to read the handout, it's in the handout. If you don't want to read the handout, I have 2 videos I want to watch. I'll send the links to you now on the group, right? All right, so we can wrap up there for today. I'm going to send 3 videos. Please watch them. All right, it's on the channel. You can subscribe to the channel as well. Let me see. Right, and don't forget the question for the roti, right? I want 3, at least 3 reasons. 4 and a bump in the uptime cost of shot. Right? So I've given you, right? You watch those 3 videos. So homework, watch those 3 videos and you're done with this topic, right? And we will go through it next week. All right, online. So that's it for today. Those who want to come on Saturday we are doing magnets. Right? So you can join the Saturday class 3 for the ones, right? All right, online. You all can log out. I'll see you all next week, please, God, right? Bye. Huh? Good afternoon, online. Good afternoon. All right, so just a quick review on what we did last day. Right, basically we focus on stationary waves last day, right? We did all the different types of stationary waves and did some examples on each one of them, right? Right, so we talked about stationary waves, right? We talked about stationary waves being two superimposed waves that produce the standard wave that looks like this, right? Here I have examples. If you have two nodes on either end, and what is called the maximum displacement again? Antinodes, right? Good. So you have nodes and antinodes here, right? These are your three harmonics if it were closed at one end, open at the next. And these are your harmonics here for both ends open, right? What did we learn about? What did we learn about moving from one to the next? What they all have in common as they move from one harmonic to the next. They all have something in common. They increase by half a wavelength, right? Right. Good. You go watch the video? Yeah. You guys saw the guy no? Let's play all four from last week to this week. Huh? Okay. Same one or some different? All right, yeah. Next year I will do it. I'll buy back a slinky long right now. That material that just spawn real fast. We could do with a rope, but all right, so that's how you produce your harmonics, right? Nice. So I think I asked you to read up on these little things, right? So these are just some applications of stationary waves, right? Some small applications. You could just take a little read on that. I think that was your homework, right? I want to go back to wave phenomena. All right. In your wave phenomena, there anybody remember the four things that waves undergo? What are the four things that waves undergo? Reflection, refraction, diffraction, and interference, right? And we're going to go in depth into interference and diffraction, right? Nice, Shabani, right? Shabani, sorry, Shabani, right? Reflection, refraction, diffraction, and interference, all right? So we're going to focus on each one of them. Some of them familiar, hopefully, right? What's the word again? Adam, what was the word? What was the word from last week again? All right. Huh? Right, the week before, and you still laughing at that? All right, so let's start with reflection. Right, let's start with reflection, right? The laws of reflection. The incident ray, the reflected ray, and the normal at a point of incidence all lie on the same plane. Everybody remember that? So you have a plane here, right? So you have a surface here, you have your incident. Oh, wait,